welcome back everybody to some more chemistry. This happens to be the last week of our journey. It started out way back in September, late August of last year, I guess, and now it's extended to this week. So we only have 2 more class periods left. On Friday, remember, we have an exam. So yeah, we're going to try to get through as much of chapter, let's see what chapter, 17 as we can. But we're not going to be able to get through the whole thing. We're going to learn some of it, and a lot of it is actually applicable to last chapter, as you saw from the very beginning of the chapter where we started talking about buffers. We're going to continue that same discussion today about buffers. If you recall, we went through this calculation using ice tables and equilibria to figure out the pH of a buffer. Okay, it turns out that we can simplify this calculation significantly. Which I'm sure that you love to hear. We can simplify this equation. If we think about this from a general perspective, we have our acid, HA. This is our weak acid reacting with water, right, to form H3O plus and a minus. Okay, this is our generalized reaction. We have our weak acid here. We have our conjugate base here. And no matter what buffer you look at, what buffering system you look at, it's going to follow this general reaction. You're always going to have some amount of weak acid. You're always going to have some amount of conjugate base. And so we can completely generalize this whole process. The Ka for this reaction is equal to the products over the reactants, which is the H3O plus multiplied by A minus divided by HA. Okay? I'm going to rearrange this for H3O plus. So I'm going to rearrange and solve for H3O plus. H3O plus, it turns out, is equal to Ka times HA over A minus. Okay? Now, if X is small, if the X is small approximation is valid, i.e., if the final number is less than 5%, if X is less than 5% of the initial concentration of HA. Okay, so if the X small approximation is valid, okay, and, so there's 1, 2, and HA is approximately equal to A minus, which is the case for our first, for our example up here. It's not always the case, but if it is the case, then this follows. Then necessarily, from this equation up here, that means H3O plus concentration is equal to Ka. Okay? Now, what if the case where this only happens if HA is equal to A minus, because you get 1 over 1, right? Or you get one value over the other value, which is identical to the first, and if they're equal, then this whole portion is equal to 1, and so this just collapses to H3O is equal to Ka. It just collapses to that value, okay? But let's consider the case where H3O plus, or excuse me, HA is not necessarily equal to A minus. Okay, this will be a pretty common occurrence. Actually, when you have HA equal to A minus, is a kind of a strange occurrence, right? Typically, they're not going to be exactly equal. What happens then? Can we make any simplifications? Remembering that we're still making the assumption that X approximation is small, is a valid approximation. Okay, so if we come back to our original equation with respect to H3O plus, we have HA over A minus here. Okay, so HA is not equal to A minus here, so this is no longer equal to 1, right? Maybe that's not a very good not equals. This, whoa, that's even worse. This is no longer equal to 1. So we cannot just say the H3O plus is equal to Ka. If we take the negative log of both sides, negative log of the H3O plus concentration, well, you guys know what that is, right? That's pH already on the one side, is equal to negative log of the Ka times the HA over the A minus. Now, you guys know that this is pH, right? And due to the identity of logs, we can actually break up this multiplication within the log into two separate logs. So this then becomes pH is equal to negative log of Ka minus log of HA, HA over A minus. Okay, now another identity of logs is that you can take these guys here and flip them, and it becomes the negative of the original log. So for example, log of A over B is equal to negative log of B over A. Okay, so I'm going to take this and make it negative, and this is pKa. Okay, so we end up with pH is equal to pKa plus log of A minus divided by HA. Now, this is a famous enough equation to get its own name, and it's named after the people that came up with it. This is called the Henderson-Hasselbalch equation. Okay, the Henderson-Hasselbalch equation. It's extremely useful, but you have to be careful. This is only valid if X small approximation is valid. Okay, this is only valid if the X equals small approximation is valid. Remember, we started off with that assumption. Okay, so when you should only use this equation, using this equation essentially allows you to skip the ice table. Notice we don't have to come up with any ice table. All we have to do is know the concentrations of A minus and HA, and we can directly calculate the pH given the pKa. Okay. This makes it a lot easier. We no longer have to do the ice tables. The ice table still works, but this is an approximation. It's a simplification. It makes it a lot easier to do certain problems quickly. Okay? So you should only use this when to use. Only use if you're confident that X equals small is valid. How can you be confident? Oh yeah, by the way, if you're not confident, use an ice table. If you are confident, use the Henderson-Hasselbalch equation. Okay. How can you be confident that X equals small is valid? If the concentrations are fairly large, okay, and if A and B are true, the K is fairly small. If these two are true, you can safely use the Henderson-Hasselbalch equation. Okay, but what does it mean fairly large and fairly small? These are very inexact numbers. Let me give you an excellent rule of thumb. If the initial concs concentrations, if the initial concentrations are at least 100 to 1000 times x, or 1000 times the value of k. Okay, then it's reasonable to use the Henderson-Hasselbalch. And as a matter of fact, it's probably better to make this 500. Okay, just to be sure. If it's 500 to 1000 times the value of k, the initial concentration, then you are completely right in saying that the x is small approximation is valid. Okay, remember, the x is small approximation is valid is taking this x, or excuse me, the initial concentration, so maybe 0.100 minus x, and it's saying that x is so tiny that this thing goes to 0, and this is approximately equal to 0.100. Okay, so you're directly comparing the value of the initial concentration with the value of x. And the value of x is completely determined by k. If k is 500 to 1000 times smaller than the initial concentration, then the Henderson-Hasselbalch equation is completely safe to use. Okay, so that's the Henderson-Hasselbalch. And it's very useful. It makes things a lot simpler and a lot faster, especially calculating buffers. Okay. Remember back when I said that buffers resist the change in the pH? Well, that's true. They resist the change in the pH. However, if you add an acid or a base to a buffer, you will change the pH by a tiny amount, depending on the total amount of acid or base that you add. Okay? And it's important to us to be able to calculate the pH change in the buffer. Okay, we want to be able to calculate this pH change in a buffer. These buffers resist the change in pH, but pH does change a tiny bit. Okay, there are two parts to the solution. Not the solution that you make, not the chemical solution, but the solution to the problem. There are two parts to the solution to this problem. Number one, the stoichiometry. Okay, how does the addition change the relative amounts of acid and conjugate base? Okay, so first you want to look at the stoichiometry and see how that changes. Second, you want to look at the equilibrium. Okay, how does the addition, calculate the pH with the new amounts? Okay, calculate the pH with the new amounts that you get from the stoichiometry. Okay, let's do an example. Say I have a weak acid concentration of 0.100 molar and its conjugate base concentration equal to 0.100 molar. Since HA is equal to AI, or A minus, that means that using the Henderson-Hasselbalch equation, or we don't even need to use the Henderson-Hasselbalch equation, we can say that the pKa is equal to the pH. Okay, now we're going to add in a small amount, so 0.025 moles of a strong acid. For example, HCl. If we add in 0.025 moles of a strong acid, that necessarily means that we're adding in 0.025 moles of H+. So the buffer has to be able to get rid of that H+, and it gets rid of that H+ through the following reaction. A H plus reacts with A minus in the solution to create HA. And yeah, that's it. Okay, so this is the added H plus. Okay, this is the conjugate base. And this is the produced acid. Or produced protonated base. Okay. So neutralizing, this is, by the way, this is a neutralization reaction. Okay, this is neutralization. Neutralizing 0.025 moles of H plus requires 0.025 moles of A minus. Okay, this is that first part here. We're looking at stoichiometry. Okay, we see that neutralizing the amount of moles that we added of H plus requires 0.025 moles of A minus. Now moving on to the second part. Basically, we need to use equilibrium to actually calculate the new pH. Actually, I'm getting ahead of myself. We need to consume 0.025 moles of A minus. So we have new concentrations, initial concentrations of A minus and HA. And the way that I like to kind of track the changes in concentration is by using what I call a ba table, like ba, you know, like a sheep. I'm not so good at doing the sheep sound. I wish I was better. A ba table. Okay, so we have B for before addition. We have an A for after addition. And we have, oh wait, excuse me. The middle one is addition. And the last one is after addition. Okay, so we have the concentrations before addition, we have the concentrations of the addition, and we have the concentrations after the addition. Now we just need to write all of our stuff up here. The concentration of H plus, concentration of HA, and the concentration of A minus over here. Before addition, we have a 0 concentration of H plus. We have a 0.100 molar concentration of HA, and we have a 0.100 concentration of A minus. At addition, we are adding in 0.025 moles of H plus. We have no moles of HA and no moles of A minus. And after addition, we have 0.00 moles of H plus again, because it's been consumed by reacting with A minus. When we take away, or when we, wait a minute, I've got something backwards here. Oh yeah, sorry. Well, that'll work. When we go through this equation here, right, we have to consume A minus. So we have to consume the same number of moles of A minus. That means that it's going to be 0.100 minus 0.025, which would be 0.075. And we have to gain the same amount of HA. So we end up with 0.125 of HA. Now what we need to do is use these concentrations in an ice table. So now we have our new concentrations of acid and base. We have just set up an ice table here. We have HA is reacting to form H3O plus, and a minus. And we just set this ice table up as we would any other ice table, where we say, okay, we have this concentration of HA and A minus. Let's find the concentration of H3O plus if we allow that to come to equilibrium. Okay, so our initial point is before equilibrium, so we have no H3O plus in the solution. So this, we use our new concentration, 0.125. We have 0.0 for H3O plus, and we have 0.075 for A minus. The change, we're going to represent the increase in H3O plus with X. So that means that we necessarily have to take away X from HA. We create X of H3O plus, and we create X of A minus. If we look at the equilibrium, we end up with 0.125 minus X. We have plus X here and plus X. 0.075 plus X here. We end up with the equilibrium expression. Ka is equal to H3O plus multiplied by A minus divided by HA. And this is equal to X times 0.075 plus X divided by 0.125 minus X. Now, we're going to assume that the X is small here. Okay, I never really gave you a Ka for this acid, but we're just going to assume that the X is small. We don't really know if that's true or not. And we can solve for the H3O plus concentration is equal to Ka times the change in, the change in the HA concentration divided by A minus change. Okay, so basically we end up with, if we assume X is small, we end up with A minus, the new A minus, and the new HA. And then therefore we can use that to calculate H3O plus. Okay, so it ends up looking basically the same as a normal equilibrium problem. And in the end, you can calculate the new pH. When we add base to a buffer, the opposite is true. Okay, the opposite is true. It should shift the other direction. Basically A minus over HA. And let's actually do this as an example with real numbers. Okay, let's do an example with real numbers. Let's have a 1.0 liter buffer that has 0.100 moles of acetic acid and 0.100 moles of sodium acetate. The Ka for acetic acid is equal to 1.8 times 10 to the minus 5. And the pH for this buffer is equal to the pKa because the moles of CH3COOH is equal to the moles of CH3COO. And we get pH is equal to pKa is equal to the negative log of 1.8 times 10 to the minus 5 is equal to 4.74. Okay, so we have an initial pH. We want to calculate the pH after adding in 0.010 moles of solid sodium hydroxide. Okay, so we're adding in 0.010 moles of sodium hydroxide. Let's do the stoichiometry first. Okay, since it's a strong base, sodium hydroxide is a strong base, it's going to completely disassociate into sodium and hydroxide, and that means that we have 0.010 moles of OH minus to neutralize. Okay, we have 0.010 moles of hydroxide to neutralize. Let's do our Ba table. Okay, so before addition, we have the number of moles of OH minus, the number of moles of acetate, and the number of moles of, acetic acid and number of moles of acetate. Now, the reaction that we need to occur here, we're going to have to react OH minus with the acetic acid this time to form H2O and the conjugate base. Okay, so this means that this time we're going to be eating up the acid instead of the conjugate base. So before addition, we have 0 of the OH, we have 0.100 moles in 1 liter of acetic acid, and we have 0.100 moles of CH3COO minus. The addition is 0.010 moles. We don't add any of these two. After the addition, we completely eat up all of the OH minus by reacting it with acetic acid, and therefore we have to use up 0.010 moles of acetic acid. So we have 0.100 minus 0.0010, and we end up with 0.090. Oh my gosh. so many zeros. Yeah, 0.090. And for the case of the conjugate base, we have to make that many moles of the base, so we end up with 0.110 moles of conjugate base. Okay, so we figured out our stoichiometry. Next, let's move on to equilibrium. And we just use these two concentration values in our equilibrium expression, where we have CH3COOH reacting with water to create H3O plus and CH3COO minus. This is our typical acid-base reaction or acid conjugate base reaction process. Okay, so now let's write out our ICE table here. ICE, we have concentration of acetic acid, and then we have concentration of H3O plus and concentration of acetate. Our initial concentrations, remember we're using our new initial concentrations, so our initial concentrations of the acid, 0.090. Again, for the H3O plus, we're treating this as 0, and then for the acetate, it's 0.110. Now, due to Le Chatelier's principle, we have an excess of this product, which is going to force the reaction back that direction. Okay, it's going to force the reaction back that direction. However, we're still going to treat the H3O plus as positive X. Okay, so even though it's shifting back towards the left, we're treating this as positive X. And I know that this is somewhat confusing, and that's okay. It's just the way that we do it. So we treat this as negative X, H3O plus is plus X, and that means that CH3COO minus is also plus X, and we end up with, at equilibrium, 0.090 minus X plus X and 0.110 plus X. Okay? Now, we can solve for Ka using the same method. So we have Ka is equal to 1.8 times 10 to the minus 5 is equal to X times 0.110 plus X over 0.090 minus X. And we're going to assume that X is small. This is a good approximation because the Ka value is less than 1,000 times the concentration of the initial species. So that means we're just going to assume that that's true, and it's going to be a good assumption. So we find that X is equal to H3O plus is equal to 1.47 times 10 to the minus 5 molar. Okay? Now this is quite small, so x is small approximation is still valid. And we find that the pH is equal to the negative log of this value, 47 times 10 to the minus 5, and we get for this 4.83. Okay, we started with, let's see, what was the pH we started with? I think it was 4.74. Yeah, we started with 4.74, and after adding 0.010 moles of sodium hydroxide, we end up with 4.83. Okay, so we've increased slightly. Okay, we've increased the pH slightly, going from, whoa. Yep, sorry about that. For some reason, my thing, wow, and it deleted, man. Oh well, I don't have to write too much. So we've increased. That was pretty trippy. We've increased the pH slightly. Okay, so we've gone from 4.74 to 4.8. Oops, 4.83. Okay, so we've increased the pH by 0.09. Is that a lot? Well, we added in a significant amount of moles and we didn't really increase the pH at all. Let's calculate the pH of 1.0 liter solution without the buffer and just adding in the 0.010 moles of sodium hydroxide. Okay, so let's calc the pH without the buffer. So we have 1.0 liters and 0.010 moles of sodium hydroxide. That means that we have 0.010 moles of hydroxide. Okay, and since our hydroxide is equal to 0.010 moles, we can calculate the pOH, which is equal to negative log of 0.010, and that is equal to 2.00. Now the pH of a solution is equal to 14 minus pOH, which in this case is equal to 14 minus 2.0 is equal to 12.00. So the pH of the solution without the buffer is equal to 12.00. The pH of the solution with the buffer is equal to 4.83. I'd say that we resisted the pH change drastically. Okay, and that's an illustration of how well buffers work. They do a pretty good job. They really resisted the change in the pH, especially in this case. And yeah, that's how we see that. Okay, I'm gonna take a break here, and we'll come back for part 2 right after this. So stretch out your legs, do some exercise, get a snack, maybe get some coffee or tea, and I'll see you back here in a bit.